Okay, this is Chapter 10, Redox, Lesson 3 in Regents Chemistry. And in today's lesson, we're going to learn how to write half reactions and to balance them, and what laws are important to remember when dealing with redox reactions. Half reactions allow us to show the exchange of electrons in a redox reaction. And I'm going to use E- for electrons throughout the lesson. For each redox reaction, we can illustrate two half reactions. One half reaction shows us oxidation, and the other one shows us reduction. An example of a reduction half reaction. The electrons on the left-hand side are gained in the reaction. So this is referred to as GER. Gain of electrons is reduction. Notice also how the charges for Fe goes down from left to right. So it's going from Fe plus 3 to Fe 0. Reduction, as we just said, GER. The charges go down because Fe gained electrons. So Fe plus 3 negative charges gives me Fe 0. An example of an oxidation half reaction, electrons on the left-hand side are lost in the reaction, which is referred to as LEO. Loss of electrons is oxidation. Notice also how the charge for iron goes up from left to right. This is called oxidation, or LEO. Charges go up because Fe lost electrons. I went from Fe 0 to Fe plus 3 because it lost or gave up 3 electrons. And when I give up negative charge, I become more positive. Always add electrons to the side of the reaction that has a higher total charge. Remember, electrons are negative. Some students just prefer to memorize that if you have oxidation, the electrons are added to the right, and in reduction, electrons are added to the left. There are two important rules that come into play for redox reactions. One is the law of conservation of mass. Half reactions follow the law of conservation of mass. This means there must be the same number of atoms on both sides of the equation. If not, you may have to put a coefficient in to balance it. The other law that comes into play is that there must also be a conservation of charge. So the law of conservation of energy. In half reactions, the net charge must be the same on both sides of the reaction. Now, although you must have the same charge on both sides of the reaction, it does not mean that they must both be 0. They can both be +1 and +1, -2 and -2. It just means that the charge must be the same. Let's look at some rules for setting up half reactions. First of all, assign oxidation numbers to all elements in the reaction. Draw brackets and identify oxidation and reduction. Begin to set up half reactions. Pull out brackets, bringing element symbol and assign charge with you. Set up as a reaction with an arrow connecting the two sides that have different oxidation numbers. The only trick, diatomics must be pulled out as a pair. This is the only time you ever bring subscripts with you in creating half reactions. The only time, and that means you have to have a Brinkelhoff. Number 4, for reactions involving diatomic elements only, balance the mass first. This is really important because usually it'll be listed as H2O2 on one side and maybe just an O on the other. So you need to balance the mass using a coefficient and make sure that there are the same number of elements on each side of the half reaction. Once it's been balanced by mass, then lastly you can balance the charge in each half reaction by inserting appropriate number of electrons into each half reaction to attain conservation of charge. Always add electrons to the side that has more positive charge. Remember, electrons are negative in nature, and net charges on each side of the reaction should be equal after adding electrons. For example, in this equation on the right, 2KCl plus 2K yields Cl2. The first thing that we want to do is assign oxidation numbers. So K is +1, Cl is -1. K here is by itself, so it's 0, and Cl2 is by itself, so it's 0. Draw brackets and identify oxidation and reduction. So we've got K plus going to K0. Well, K plus going to K0 is becoming more negative, so it must be gaining electrons, and this is reduction. I'm going to label this RED, reduction. And then we have Cl minus going to Cl0. So this is becoming more positive, therefore it must be losing electrons, and this is oxidation. So we've already done number 1 and 2. Begin to set up half reactions. Pull out brackets, bringing the element symbol and the assigned charge. So let's do K first. So we have K plus going to 2K. So the first thing that we want to do is balance our mass. So we're going to put a 2 here. And this is going to K0. So we have 2 times a +1 versus a 2 times 0. So in this case, we would have to add 2 electrons to the left-hand side. So 2K plus 2 electrons yields 2K. So a +2 and a -2 equals 0, which matches my 0 on the right-hand side. My other equation is Cl minus going to Cl2, 0. Well, the first thing that you want to do is balance your mass, so you're going to put a 2 here. So 2 times -1 is a -2. So I need to add 2 electrons to the right side. So now I have a -2 on the left and a -2 on the right. So K plus going to K0, this is my reduction reaction, and Cl minus going to Cl0 is becoming more positive. This is my oxidation reaction. Okay, so let's do a couple practice problems. In example 1, we have magnesium plus zinc chloride forming zinc chloride and zinc solid. Remember that most single replacement reactions are in fact a redox reaction. So we'll assign oxidation numbers. Mg is by itself at 0. Chlorine is -1 times 2 is -2. Remember, if this has to equal 0, then zinc must be +2. Over here, chlorine is -1 times 2 is -2. I need a total of 0, so this has to be +2. And zinc is 0 because it's by itself. So for magnesium, I'm going from Mg0 to Mg plus 2. I'm becoming more positive, so I must have lost electrons to do that. So this is Leo. Loss of electrons is oxidation. So this is oxidation. Over here I went from Zn plus 2 to Zn0. I'm becoming more negative, so I must have gained electrons. So this is Ger. Gain of electrons is reduction. So here's my reduction. So now we're going to pull out our elements. Mg0 went to Mg plus 2. So I have a 0 versus a plus 2 charge. I need to add 2 electrons to the right. So I have a plus 2 and a negative 2, which is 0. My Zn plus 2 goes to, on the right side of the arrow, Zn0. So I have a plus 2 versus a 0, so I need to add 2 electrons to the left because a positive 2 and a negative 2 matches my 0 on the right. Here's an example where you have to balance masses. First of all, there are some charges missing here. This should be a plus 2 on the Hg, and this should be a negative 1 here on the iodine. So they have charges that came with them. So the rest of our charges, Hg is by itself, it's 0, and I2 is by itself, it is 0. So let's see what's going on here. We have a positive 2 going to 0. I'm becoming more negative, so I must have gained electrons, and this is reduction. I have I minus going to I0. It's becoming more positive. It must have lost electrons. This is oxidation. I'm going to pull out and write my oxidation half reaction. I'm starting with I minus. I wind up on the other side of the arrow going to I2, 0. The first thing that I must do is balance my mass. So I'm going to put a 2 in front of this. So I have 2I on the left and 2I on the right, but a 2 times a negative 1 gives me a net negative 2 on the left. Therefore, I need to add 2 electrons to the right. So I have a net negative 2 on the left and a net negative 2 on the right. In my reduction half reaction, I'm going from Hg plus 2 to Hg0. So I am decreasing, becoming more negative. This is my reduction. And I have a positive 2 on the left and a 0 on the right, so I need to add 2 electrons to the left. Positive 2 and negative 2 is 0, which matches my 0 charge on the right. And the last example, we're going to balance charges. I have Cu, which gets assigned a 0. Ag is plus 1. NO3 is minus 1. I don't have to assign oxidation numbers individually to nitrogen and oxygen because the nitrate ion stays intact on both sides of the equation. This 2 on the right over here tells us that copper was plus 2, and we know that nitrate is minus 1. And silver on the end here is by itself, so it's 0. So let's take a look at what's going on. I've got copper going from 0 to plus 2. It's becoming more positive, which means it lost electrons. Leo is a loss of electrons is oxidation. And my Ag went from plus to 0. It's becoming more negative. And we know that Ger, a gain of electrons, is reduction. So let's write our individual half reactions, starting with our element that was oxidized, Cu0, turned into Cu plus 2. I have a 0 versus a positive 2 charge. I'm going to add electrons to the side that has the higher total charge. So I'm going to add 2 electrons to this side. A positive 2 and a negative 2 is 0, which matches what's on the left. And for my reduction reaction, I have Ag plus going to Ag0 on the right. And I'm going to add my electrons to the side that has the higher total charge. So I have a plus 1, so I'm going to add 1 electron here. In this one, remember, we are practicing to balance charges. Notice that I have a -2 charge here and a -1 charge here. So those are not balanced. What I can do though is multiply this reduction half reaction by 2. So I'm going to do that down below. I'm going to multiply it by 2 so that I get a total of 2 Ag plus 2 times 1 plus 2 electrons yields 2 Ag0. Now truly what I would be doing at this point was I'd be taking my other reaction, Cu0 yields Cu plus 2 electrons. Because my electrons are on opposite sides of the arrow, I can cancel these out. And my final reaction would be 2 Ag plus Cu0 yields Cu plus 2 Ag0. And it doesn't matter what order you write these in. You can have the Cu first and then the Ag and the same on the right side of the equation, as long as what's on the left appears on the left and what's on the right appears on the right. Okay, that's it for lesson 3. Have a great night. See you next time.